So good evening, everyone. So this is week 5 of the weekly interactive live session. So as usual, I'll introduce myself. I'm Harish. For those people who are joining new, I'm a PhD scholar from IIT Hyderabad, and the objective of these live interactive sessions is to help you understand what has happened in this week in the videos, in the NPTEL videos, through solving questions, through addressing questions, um, so that the concepts might become a bit more clearer, right? So if you have any questions, you can ask me. If I know the answer, I'll tell you. If I don't know the answer, I'll find out and I'll tell you. And if anybody knows the answer, they can tell the answer. Meaning this is going to be a healthy discussive session. And in the last week, what we did was we solved some numerical questions. Right? We solved token bucket algorithm questions, and we understood them in a simplified way. However, this week, I believe all of you would have gone through the videos, right? And it is mostly about the history of the internet and understanding certain concepts, understanding the way the internet evolved, and why the internet is the way it is right. Why the network is the way it is right now. Right. Although it is not possible for us to go through all of that, some key highlights I shall talk about it in the beginning, and we shall go through some questions. And like usual, there are two sessions. One happens on Friday, the other one happens on Tuesday. You're free to join either both of them or none of them, because these sessions will be recorded and you can see that on the link that is presented to you in the NPTEL submenu on the left side. So today we shall possibly be going through these 10 questions, right? So the first one is, what I'm going to do is I'm going to go through all of these questions, and I'm going to make sure that you know what is coming up, right? That you can you know what to expect this session. So this is a question about layering principle. So layering is something that all of you must be familiar with at this by this time. Right. So this is the layering principle, and there's a slightly different take on the layering principle here, which we shall go through. And this week it is completely theoretical. There are no numerical questions to be solved. It's only concepts, and they're two very concepts which have to do with some factual history as well. So this is something called the layering principle. Of course, this is common knowledge. We have 7 layers or 5, depending upon which stack you use. Spoken about this in the previous classes as well. And the next one is NCP. So this is something to do with a very early internet, so if you would like to call it that. So we look at some historical concepts and answer questions based on it. These are all very factual questions. There is nothing much to discuss here. Right. And we also talk about certain scientists who came up with certain theoretical rules or laws, and their vision of how the internet was going to be. And depending upon that, there is a question. You need to choose which of the following is not one of the internet working principles was envisioned at that point of time. Right? And what is IMP stands for? Once again, this is going back to the ARPANET days. So for those of you who might not be familiar with what ARPANET is, you can look at the videos, the class videos, or you can just type ARPANET and you'll know. It's one of the very first internets of the world. As if it might not be right to call it the internet, but yeah, this is one of the first networks, widespread networks in, in existence, you can say. And what was the first successful message that was exchanged on the internet, on the early internet? So whatever was the early internet, right? So what was the first word exchanged? Was it hello? Was it hi? Was it login? Or was it welcome? Let's see. And which of the following is not true about the layering principle? Once again, we are having the layering principle. So it's just a slightly theoretical take on what we have learned so far practically also. So which of the following statements is incorrect about network protocols? So we know what a protocol is, but I'll reiterate on that again. And what is a protocol and what is it that it is not? All right. So this question is asking which of these does not speak about network protocols. You should see that. Again, middle box was something that I introduced, I think 2 weeks ago. So this is specialized equipments that do some kind of functions in the internet. And today we'll look at what NAT does. NAT is a type of middle box, and is like what they're asking is which of these is not a characteristic of a middle box. Okay. I'll speak in very simple terms. So for people who are familiar with this, it might be too basic. For people who have not gone through computer networks properly, or who have not at all gone through computer networks, this might be helpful to them because I'll talk about it from a ground up level. So which of the following aspects is not the reason for the internet ossification? So what is the internet ossification? There are certain things that come into the picture in terms of evolution of a particular technology. So internet is also one such kind of a technology that has gone through this ossification phase, right? So what is it, and what is the answer for this question? Let's see. So which of the following is not a solution to break the internet impasse? So what is this internet impasse? We should look into it and we can derive what the answer for this is. All right. So what I shall do is I shall switch to the screen. Just give me a moment. I'm having some technical difficulty. Right, I am sure the screen is visible to everyone. Okay. So just a quick reminder of what has been taught in this week 5 of the videos. Okay. So you had a brief history of the internet, right? So what you possibly would have learned from that is the internet evolved. And when I say that the internet evolved, it grew out of necessity. Like they say, necessity is the mother of all invention, right? Right? So this is how the internet also evolved. um, One fine day, somebody from some institute wants to connect his computer to someone else over here, right? And let's say that he has connected. Next, another person joins the fray, and then he says he wants to connect his computer to his computer. Okay, done. Next, another person, right? So far, it's manageable. But imagine if the number of people who are connecting start increasing and they become thousands, hundreds, or thousands, right? So from a layman's point of view, you put yourself in the shoes of these people. If there are 100 nodes, or rather if there are 100 nodes, or so one person has a node, right? So I'm going to call them as a node. So there are 100 nodes. Let's say 1, 2, 3, 4, like this. So if this person wants to communicate with this person, it be connection here, connection here, connection here, connection here, connection here, connection here. So this is a layman's way of doing it, right? But even a small baby will tell you that this is not the best way to do it. So as the number of people increased, the more they thought of this phenomenon, which was evolving of networks. Basically, we are networking in between multiple nodes. So multiple schemes were devised. So one of that is circuit switching. The other one is packet switching. So the major difference between both of these is the way in which the connection is established, right? So if this is the topology, just for example, okay? If this is the topology. If A wants to communicate with B, then what will happen is this whole circuit will be reserved for A and B, right? But in this case, you have packet switching, which means the input to the network is going to be chunks of data, but some chunks can go this way, some chunks can go this way. In the sense, it's a more flexible way of doing things. And finally, of course, these 5 chunks are reconstructed at the end. So in a layman's way, this is how you can understand circuit switching and packet switching. Circuit is you're completely reserving the whole area, or rather the whole route itself. Okay, and this is across for multiple people. So let's say there are some more people as well. Then maybe this link can hold 3 or 4 people. Let's say. That's how it used to happen. right? But but eventually we moved from circuit switching to packet switching. Packet switching. Right? So the moment we came into packet switching, there came many myriad of protocols and services also. Okay. So the internet was evolving at quite a rapid pace. Right? So the internet was growing, right? But what happened was the internet grew, but it became stubborn. And what that means is it was not happy with change. Now, what could this possibly mean? Okay, I'll give you an analogy. I think all of you are computer science people. So, okay, maybe not. I don't know if all of you are from computer science background. I thought the analogy could be from the networks, sorry, the programming point of view. Or, right, okay, let us look at it like this. You have three cities, city 1, city 2, and city 3. Okay. Now, one fine day, these roads were laid. Why were these roads laid? These roads were laid in order for people to travel on it. Okay. So these roads were of thickness 10 meters. Okay. This thickness I'm talking about 10-meter thickness. So which means only certain, okay, let's say 5 meters or even 4 meters. Only a certain dimension of vehicles can travel. Okay. So people are happy. Number of people in city 1 is, let's say, 100K, 100K, 100K. So this is in year 2000. Okay. So people are happy. It became 2001, 2002, 2003. Okay. People are still happy. They're happy in 1, happy in 2, happy in 3 because they were able to travel, they were able to do everything. But let's say in the year 2007, the number of people living in the city became 1 million, 1 million, 1 million. Okay. Now, these roads were causing a lot of traffic congestion, because previously there were 100k basically 1 lakh. Okay? 1 million is 10 lakhs. Previously it was supporting it, but now the moment the demand increased, number of people using the road increased, these roads were not sufficient. So when were these roads laid? These roads were laid in the year 2000. Why were they laid with such thickness? Because at the year 2000 they thought, okay, this is going to be the requirement for now and for 4 or 5 years in the future. They looked ahead only for 4 or 5 years. Let us lay the road, let people use the road. But now in the year 2007, people are not happy. So this becomes a problem. Road congestion becomes a problem. So what do? The administration brings new rules. And these new rules could be things like at in the morning, traffic can go only in this direction. From city 3 to. Another rule is people not buy cars of size greater than Alto. I hope all of you know what the size of an Alto is. So why are such rules being put? It is because this is the existing infrastructure. Correct. There are two routes to solve this problem. One is optimize what you can put on this road. Create new rules, create new methodologies, and this is what is called protocols. So what do these protocols do? They tend to optimize what we have within the existing infrastructure. So this is the key point. Correct? So the first option is optimize within the existing infrastructure. So this is a one option. Second option is upgrade the existing infrastructure. So which of this is cheaper? First one is cheaper because the administration does not have to do a lot of things. They're basically optimizing what they're able to put into these roads through different timing rules or through controlling the kind of cars that you're sending into it. So the analogy for cars here are packets. Okay. So this is not a very realistic example, but it kind of drives into your mind as to why the internet is not happy with change. All these roads, right? So if you look at the internet, some protocols were defined based on which the internet was designed. By internet, I mean routers, switches, and all the devices that connect nodes. Okay? Now you have invested a lot of money. Okay, capital is money basically. You've invested a lot of capital into creating these infrastructures. Okay, and these infrastructures, router switches, they were built based on these protocols that existed when they were implemented or when they were manufactured. These routers and switches work well for existing protocols. Now let us say some researcher came up with a new protocol. And this protocol improved congestion by, let's say, just giving a ballpark figure, okay, by 1% or some particular value. So basically, someone said if you do the protocol in a particular way, you can make networks better. Correct? Now the question is, can you implement this idea on the existing internet? Think about this. Answer is no, because this new protocol requires features that are not supported by the existing routers and switches. So if they want to implement this feature, which is going to give them a 1% increase. It is not as simple as installing a new software. It is not as simple as this, is what I'm trying to say. Because if on your system, on your computer, if you want to install a new software, all you do is you download something and then you install it. But on the internet, upgrading something is not as simple as it seems, because it involves a lot of proprietary hardware which come from multiple vendors. There is heterogeneity there. We'll look at all of this. But essentially, I gave this example to make you understand why the internet is stubborn and why change is difficult in the internet. Okay, right. So where were we? We're talking about the evolution of the internet, right? So for details, you can look at the video. I'll just give a layman's view of what happened in a very abstract way. So as these networks grew, they became resistant to change. Okay. And this is what is called ossification. These are all synonyms. Ossification means it's hardened. So when something hardens, it is not flexible. Right. So that is what happened in the case of the internet. So because of this, we can say that things looked stagnant. Even the smallest of changes were difficult to deploy. An example for this is IPv6, right? Even now, I think now there is support for IPv6, but 1 or 2 years ago, if you noticed, then I mean, not all routers supported IPv6. Even now, I think most of the home routers don't support IPv6, if I'm not wrong. So it's still something that is coming up. IPv6 was introduced many years ago. This is still there also. And the growth of the network was always influenced by economics. And by economics, I mean capital gains, and large corporations who had competing interests. Right. So what is the consequence of this ossification? Yeah, by the way, so what I mean by this is You would have thought that networks evolved as due to necessity only. Of course, that was always a part of it. Necessity was always a part of it. But once companies, like let's say company X, company Y, some networking companies or Cisco, Juniper, and all these, or HP, all these networking companies, right? So I'm not pointing out any company. Once a company starts manufacturing routers or manufacturing network equipment, what tends to happen is they start gaining market share. So when they start gaining market share, more market share means they can introduce new features. Just for an example, if 90% of people, customers, use equipments from a company A, let's say, okay, not naming a company, then what the company A will do, they will possibly introduce a new feature that, let's say, increases speeds or something similar. Okay, or rather, let's keep it simple. That gives you more control over your own network or something like that. Let's say they've added a new feature. I'm not able to exactly say which feature uh, looks realistic, but let's say something they've done something. And they say that between a router from company A to another router from company A, the speeds will always be 10 Mbps, 10 whatever, 10 Mbps. But if you go from company A to company B, it will only be 5. In the sense, they say that connections between two routers of the same company will be more faster. So once they do this, then there is no chance for company B to enter into the picture. Who Nobody is going to buy company B. So company A is going to rule the market. And in that process, what they've done is they've modified the internet protocols in order to suit their needs. That's all. So this is where competing interests come, and the internet also evolved. So in response to this, what happens? Company B comes and says, "You buy my routers, I'll give you 15 Mbps." So all of these innovation is happening. Yes, agreed, but it is happening at the cost of modifying the internet, modifying protocols uh, with uh, a view towards gaining more market share, gaining more capital, and of course, trying to dominate the the ecosystem. Right. So this also leads to something called fragmentation. There is no uniformity between networks. If multiple people say my routers work in a particular way, the other routers work in a different way, right? So once again, so what is the problem here? It is ossified. Internet becomes ossified, right? But ossification is a very serious problem. Why? Because once the internet is hardened, once it's inflexible to change, then fortunately innovations are discouraged. New ideas may remain as ideas, even though they offer significant benefits. Okay. Right. So in a way, it stops innovation. Um, Basically, this problem is not endemic to networks only, but it is more severely seen in networks because networks is something that spans across geographies. In that case, upgrading equipment or making sudden changes to the topology is not easy. It is very difficult. Okay. So basically, this is what you must have learned in the previous lectures in the NPTEL in the NPTEL videos, right? So just a quick reminder before we go to the questions. Layers. What are all the layers? So we have the ISO consistent interface layer, layer. So what are these? There are 7 layers here. Application is layer 7. Presentation 6. Session 5. Transport 4. Network 3. Data link is 2. Physical is 1. But in practicality and in practical scenarios, we use something called TCP/IP model. Okay, this is application layer is 5, transport is 4, network 3, data link is 2, physical is 1. Right, so this becomes a block. This is as it is. As it is. The link which is equal to 1, 2, 3, 4, 5. Right. Okay. So whenever a packet so whenever a packet, let's say, wants to go from this computer to this computer, right? Whenever a computer wants to communicate from this computer to this computer, it generates the data. The data goes to data is originating from the application layer, correct? And this application layer data is encapsulated by the transport layer, right? And then it goes to the network layer. Right? So at every layer, each layer adds its own information, and this information is used for multiple services on the internet or functions on the internet. Right? So if you want to look at it in a slightly formal manner, there is something called protocol data unit and service data unit. Protocol data unit and service data unit. Okay. So in bare bones level, let's understand this with a particular small example. Let us say there are 3 layers here. Layer 1, let's say layer 3, let us say layer 5 itself. Layer 5, layer 4, layer 3. Okay. So whatever data so with PDU, SDU, PDU, SDU. So whatever data is given as input to a layer, okay? Whatever data is given as input to a layer is called SDU, service data unit. Keep it like this. Put to a layer is SDU. So what happens when there is an input to a layer? This layer adds its header, right? So once the layer adds its header, this whole thing becomes something called PDU, correct? So it is, in a way, you can say PDU is equal to header plus SDU, all right? Okay, this is one trivial equation. So this is, let's say, and this PDU that is formed is sent to the next layer. But what happens here? The PDU of a higher layer is coming to a lower layer, and this lower layer is going to add something onto it, correct? So once the input to any layer is always called SDU, PDU becomes SDU. That's it. Now what is added? Header is added. Now what does this become? It becomes a PDU again, protocol data. Now this PDU is sent to the next layer. And what does it become? It's called SDU. What is added to it? It's the header. Right? So this process goes on. So input to a layer is SDU. Header plus SDU is equal to PDU. And what is the input to a layer? Input to a layer is again PDU, because the PDU in the end is what is going to the lower layer. Right. So in this context, let us answer the first question. Please select the correct answer on layering principle. Okay. So n denotes the layer number. Okay. So we go from higher layer to lower layers. What is this? What are the first? The first one says layer n plus 1 PDU is equal to layer n's SDU. So is that right? Layer n plus 1. Now let us say, let me put a value for that. Okay? Let me put a value of 4. N is equal to 4. Right? Because this equation has layer 3, layer 4, layer 5. So n is equal to 4. It says layer 4 plus 1 PDU is equal to layer 4 SDU. So what is 4 plus 1? Layer 5 PDU is equal to layer 4 SDU. Let's look at the diagram here. Layer 5 PDU is this. Layer 5 PDU is this. And layer 4 SDU is this. Aren't these two equal? Yes, they are equal. So this is correct. Now let's not leave the other ones aside. Let's go through the other ones also. I'm gonna just plug in 4 here, okay? 4. So what this becomes, layer 5 SDU is equal to 4 PDU. So layer 5's SDU is equal to layer 4 PDU, is it? Layer 5 SDU is what? This is layer 5 SDU. And which is layer 4's PDU. Layer 4's PDU is this. That is pretty much a huge distance between this and this. So it's wrong. Next. Layer 5 SDU. Why is it 5? Because I put 4 here, right? That's a 4. That's a 4. Layer 5 SDU is equal to header of 4 plus layer 4 PDU. This says layer 5's SDU. Layer 5's SDU is this part, right? Is equal to header of 4 plus layer 4 PDU. Header of 4 plus layer 4 PDU. It doesn't make any sense. Where are these? These are in multiple different places. So this is also not correct. So if you do the same thing here, say a layer 4, layer 4 SDU is equal to header of 4. I'm taking n as 4 just for this example. Again, just reminding you. Layer 4 PDU. Layer 4 SDU, where is layer 4 SDU? This is layer 4 SDU, right? Is it equal to header of 4 plus layer 4 PDU. Is this equal to this plus this? No, right? This is also wrong. So what can be right here is PDU of n is equal to header of n plus SDU of n. If you put this in normal words, if I say PDU of layer 4 is equal to header of layer 4 plus SDU of layer 4. This is good enough, right? So that is the right equation there. This is wrong, this is wrong, this is wrong. Question A is correct. And there is also one more question that concerns architecture. Sorry, the layering principle. Right? We saw this in the beginning. That's why we went through all the questions. That is question number 6. This question says, which of the following is not true about the layering principle? So which of the following is not true about the layering principle? Right? Not true. The first one says, helps for modular and hierarchical implementation of communication functions. In this whole sentence, you see this word modular and hierarchical. Right? So communication functions are nothing but the code that you use, that you write to enable communication between point A to point B. So how do you write that code? How do you write these communication functions? You call libraries. Right? And these libraries are nothing but they are modular. If the layering principle was not there, it would not be easy to unify and make things uniform across multiple endpoints. Right? So there is this hierarchical. Hierarchy is the vertical hierarchy that we have, right? Layer 7 to layer 1. And there is also this modular implementation, right? So this is true. It is modular. Layering principle makes things modular. So the lower layer provides a specified set of services to the upper layers. Is this true or false? You have layer 5, layer 4, layer 3, layer 2, layer 1, right? So layer 5 generates some data and sends it here. What does 4 do? It adds a header. So what is there in this header? This header contains some information. What does layer 4 add? It adds port numbers. So what do port numbers do? They ensure delivery to the right process on the other host. You would have studied this in the basic computer networks course. So these port numbers, right? TCP port number, UDP port number, and all the and all the similar like HTTP and all these port numbers. So the packet is sent to the correct service. So in a way, layer 4 ensures correct delivery in the host. Okay. So when you go one step down, The same goes here, and this is the previous fourth header. You get a three header also. This is network layer. Layer 3 is network layer. So what does this add? This adds IP addresses. So what do they do? IP addresses ensure correct delivery to the host. Previously was inside the host, where should the packet go to? That's what layer 4 was doing. And now layer 3 is doing which host even it should go to. So essentially what is happening is upper layers depend upon the services offered by lower layers. 5 is an upper layer. It depends on 4 to deliver it to the correct process. And it again depends on 3 to deliver it to the correct recipient or the correct node itself. Correct. So this is true. So protocols at a given layer communicate indirectly across adjacent nodes. Okay, so what are adjacent nodes? Let us say this is the scenario. Layer 5, 4, 3, 2, 1. I spoke about this in a previous session also. 5, 4, 3, 2, 1. Okay. 3, 2, 1. Why is there only 3, 2, 1 here? Because this is a router. The router does not have to look into layer 5 or layer 4 for that matter in an ideal world. So what does it do? It doesn't even implement those stacks. I mean, these are all this is the IP stack and the network stack, and the network stack is not implemented completely. So in a way, a packet being sent from here, right, is going to go here and this is going to read number 3. This is definitely going to read the layer number 3 to find out which interface to send it over. So in a way, protocols at a given layer, its IP is a protocol at this layer, right? It communicates indirectly across adjacent nodes. So it communicates across with this and with this basically. Although it is not direct communication, they take the information and they make some changes onto it and then send it further. So in a way, this particular layer establishes a common understanding across multiple adjacent nodes. Right, so this is also true. And the final thing is vertical communication does not require any mutual understanding between the different protocol layers. Okay, so this is vertical. Vertical is top to bottom or bottom to top, anything. But in this case, we are talking about top to bottom. If you look at the host side, you have to talk about bottom to top. But let's look at just top to bottom now. When I'm sending the data here, right, it is adding a header field here. Okay, so there are certain instances where the layer 3 has to add certain data, like for example, whether it is TCP or UDP. So this is added in a particular separate field inside layer 3. So how does it know whether it's TCP or UDP? The information is coming from the top. So there is some level of understanding between different protocol layers, right? In order to communicate and in order to give the right encapsulation. It's not like I've given this data, now you do whatever you want with it. It's not completely like that also. There is some level of communication. How many bytes to strip off when you're going in the opposite direction. All of these details are there. So in a way, there is a requirement of mutual understanding between different protocol layers. So this is wrong. So the answer to this question is D. Okay. Correct. So now let's move on to question number 3. Sorry, oh, we've not done 2 yet. Okay. Now this I think is a very historical question. In current world, I don't think many people would have heard about NCP. Right. So the answer to this is network control program. Okay. So what is this network control program? So this was during the days of the ARPANET. So this was around the time 1970s, I think, between 1970s and 80s. Right. So what this network control program did is it acted like a transport layer of the protocol stack. So in a lot of ways, NCP, this program or protocol, was like the older version of TCP. It was used at that point of time, right? So when the development of TCP started, right? They needed to refer to the previous version of TCP, and then they named it Network Control Program. So that's pretty much what this is. There is nothing big on this. There's no point in understanding what Network Control Program did. So in a nutshell, if you want to know what this is, it was the name for the software on hosts which implemented the network control protocol. And where did this happen? This happened at the ARPANET. So this was usually referred to as NCP, and right. I think there's no point going any further on this particular NCP. It's very historical. It's a very actual and historical question. Right, so this is directly from the lectures, I think. So if you look at these two scientists or people who defined how the internet should work, right? They gave certain theories, or they gave certain rules as to, okay, this is how it's supposed to work for it to achieve so and so. So that was what they did, and in that they have spoken about something called a universal addressing scheme. It has to be universal because if I say my address is ABC and somewhere else they're saying the address is 123, that is not universal. You have to define that all the addresses have to be defined by A to Z. Right? So everybody will follow that. So everybody can understand each other's address and you can go from point A to point B. And best effort service model, we've seen it, right? We've seen it in the previous class. You try to do as good as possible. If you can't, then you won't be able to. That's fine. Right? In terms of congestion control, or if you want to satisfy some requirement, you try to do it. The network will try to do it. But if not, then it will drop the packet, right? Something like that. And stateful network for effective resource sharing. So when it comes to stateful network, so a stateful network is a very recent term. It's a network which remembers a lot of things about the packets that it sees. Right? So when this was defined, this was not a part of the definitions. So this is the answer. And decentralized control and minimal autonomy. This is also right. The control is not centralized, although it is in a lot of ways coming back to the centralized control through STN and other things that you'll learn in the coming weeks. When it was defined, it was considered an ideal property of the internet. So the answer is C. Now, this is another historical question. What does IMP stand for? So the answer is interface message processor. Interface message processor. IMP. So what was this? So again, this goes back into history, right? So so it was, if you want a definition of it, it is basically was a packet switching node. Correct? A node means it's basically a device, let's say. That was used to interconnect networks. And where did this happen? Again, ARPANET. Around 1960s or around 1960s to 1989. This is according to Wikipedia. So essentially what this is this is a device, right? This was the predecessor of a gateway. This was the predecessor of gateways. It was the first generation of gateways. So what are these called as now? Gateways are nothing but routers. So your IMP was a very old version of the router. Okay. So an example for an IMP, if you want to search for it, you can search for it. It is the Honeywell TDP 516 mini computer. How complex the naming was. Now this had some special purpose interfaces and software. So essentially the IMP and the software, all of this was published in RFC. This was RFC1, first RFC, I believe. Right. So nothing much to talk about here. It was just an old version of the router. It was used to connect between multiple nodes. There's an IMP kept here. Traffic goes through the IMP. That's pretty much what this is. Right. So we move on to the next question. Right. So question number 7. So which of the following statements is not correct about network protocols? Again, this is not correct. So protocols define the format of the message to be communicated. It's obviously right, because let us say IP. We studied IP last time, right? In the last session. An IP has source IP, destination IP, right? And then it has something called the DSCP also. I think it's in the first of. It has a particular format, basically, right? 32 bits, 4 bytes. You had something called the DSCP, and you also had the source IP. Source IP, destination IP. And so a protocol would mean that this is the format of the message, the format of the header field, correct? This is the format of the header field, and a header field is also a part of the message. So protocols define the format of the message. So message also contains header field. And who defines the header fields? Protocols. So yes, it is true. So protocols determine the conventions of communication. Okay. What is an example for that? Let us say TCP. Okay. So what is the convention in TCP? If this packet is of TCP and I'm sending it from here, here, I'm sending it from here to your friend, okay? And I'm sending it's going, and here the packet got dropped. It's lost. So what will TCP do? It won't sit quiet. Once it does not get a response, an acknowledgement from your friend, it will say, okay, I've not received an acknowledgement, so I'll send the packet again. So it will send the again. So what is this? This is a communication convention. So this is the behavior of the communication. Let's make it simple. Behavior of communication. TCP behaves like this. Now, if you take UDP, what will it do? It is dropped. It is dropped. UDP does not do anything. Does not care whether the packet was delivered or not. Hmm? It does not care at all. Right? So yes, so the answer is correct. All of the network protocols have to be accepted and published by the standardizing organization like IETF. So you may be compelled to say yes, it's true. Why will you be compelled to say that? Because protocols have to be accepted across multiple nodes for it to be usable. So if I say in a network like this understands red protocol, red protocol, red protocol. This understands only black protocol. The problem here is this cannot communicate with this because this person has used a different protocol. This is a different protocol, a different protocol, a different protocol. So how do you stop this? You bring in an organization called IETF, right? Which tends to release RFCs, I think. Yeah, which tends to say TCP means it's supposed to behave like this. UDP means it's supposed to behave like this. Okay. So based on which everybody will refer this IETF document and they will implement either all red or all black. And everybody can communicate. So you'd say the answer is yes, correct? But not necessarily. Let's say me and my friend want to communicate such that nobody knows what I'm doing. I will create my own protocol that only me and him can understand. These are called proprietary protocols. Mostly these are at the application level, application layer. An example would be, I think, Skype. So as far as I remember, I don't think we know what how they implement their protocol, but how does it work? Because in your computer you have the Skype software, and in the remote server also, it is their own servers. So if the endpoints are under single control, then you can implement your own protocol, and you don't need to get it ratified by the IETs. You don't have to. So this is wrong. This is not correct. The answer is this because it's incorrect. And of course, now the other thing is protocols define the procedures and sequence used to exchange messages. Right? So this again is the same. D and B are the same. Exchanging messages, communication. It's all a part and parcel. How does communication happen? It happens by exchanging messages. Okay. Now moving on to question 8. Now this is a very interesting concept, middle boxes. I introduced middle boxes some time ago in a previous lecture. I think one of the very first lectures I spoke about middle boxes. So what is this middle box? Right. Let's talk a little bit about it, and then let us go into the The definition of a middle box is that performs functions other than the normal standard functions of an IP router. Okay, this is what it is. An intermediary device that performs functions other than the normal standard functions of an IP router. This definition, I've taken it directly from your course video only. Right. So what does an IP router do? It performs IP routing this much you would have understood from the course till now. Right. So this is directly this. So definitely the answer is this. But let's not stop there. We know the answer is this. That means a middle box is an intermediary device that is placed between the source and the destination hosts. Yes, right. If this is the source, destination, a middle box can be placed over here. That's why it's called middle box. They perform non-standard networking functions. Yes, they do everything other than IP routing. So they're all called non-standard networking functions. And they also include stateful networking functions, which means they remember state. Okay. Now, what are all the examples of a middle box? If we take some examples, we have load balancer. Then we have firewalls. And then we could also have intrusion detection systems. And then we can also have network address translators. They're called NATs. So you might know what load balancers are for if there are multiple paths. So this middle box will send packets in such a way that the links are all balanced, meaning the link utilization is balanced. If it sends all the data in just one path, then these are unused, even though I could send it through these things. That's what load balancer does. Firewalls is something that either that stops the packets based on certain rules. If suppose it detects some malicious actions or some packets that look malicious, it might stop the packet right here. Those are all what firewall does. And intrusion detection system is also something similar, but it does a little bit more complex functions than just firewalls. Right? Just than firewall. Firewall is generally rule-based, static rule-based. Next is network address translations. So what is this network address translation, right? So we all know that the IP address space is 2 to the power 32, right? So it's pretty much all of the IP addresses are exhausted when they are all used. But still, the number of devices that we see are multiples of the available IP address. So how does it still function? How does it still work? Okay, let's take a look at the example. And with the example, you'll understand how NATs work, network address translations. Okay. So let us look at a topology like this. This is one computer. The IP address of it is 10.0.0.1, 10.0.0.2, 10.0.0.3. Now there is this server sitting over here, and the IP address of the server is 128.9.40.186. Okay, and if you've these IP addresses, right? Let's start with 192 or 172 or 10. So these are all called private IP addresses. So you would have noticed if you are in your home, if you type ipconfig on your system, you will have a particular IP address. So currently, if I see mine, that's it. Right. So these are all IP addresses that are reused across multiple locations. I mean, let's say 10.0.0.1 is not unique across the internet, because in your home, your device might have 10.0.0.1. The same IP address will also be in your neighbor's house. So the difference is there is a router over there, or rather, there is a middle box over here. Okay, sometimes the router also has middle box functionalities. Now, so imagine that this entity wants to communicate with this server, right? The server is operating at port 80. What is port 80? It is HTTP. Right. So what will it send as the source and destination IP address? So this will send, source would be 10.0.0.1. What will be the port number? Some random port number. The destination is 128.119.40.186, correct? And what will be the destination port number? It will be 80. So this is what this will construct, and this packet will go like this, and it'll hit this part. Okay. So now what happens here is, if you're going to send the packet as it is, this 10.0.0.1 is not unique to this network. It is used in multiple places. So this 10.0.0.1 cannot be routed upon in the core internet. So what can be routed upon is the IP address that this middle box or this router has. So what is it? This is called a public IP address. Let's say this is 138 76, 29, 7. Okay. So in a way, this box here has to make some changes to the packet. So how does it do it? It has a NAT table. So the NAT table, it divides it into WAN side and LAN side. So what is WAN? Wide area network, and that is this side. What is LAN? Local area network, that is this. So as soon as it gets this packet, what it is going to do, it is going to say on the LAN side 10.0.0.1, comma 3345. Right? That's what we sent here. Please map it to 138.76.29.7, comma some port number, 5001. So what it does to this packet, it takes it, it puts this entry, and then it converts it, and the final packet will look like this: 38, 76, 29, 7, 5001. Destination is 128, 19, 40, 186, 80. So the destination is not touched, but the source has been changed. Notice, what has it been changed to? This has been changed to this. Correct. So now this packet reaches here, and the packet is processed, and you're getting a response from here. What will be the response from here? The source IP would be 128, because it's getting a response from here, right? So 119, 40, 186, 80, correct? Whatever was in the source will become the destination now. The destination will become the source. What will be the destination? So according to this system, it does not know the existence of 10.0.0.1. It only knows that there is some IP address 138 because that's what reached it. Destination is going to be 138, 76, 29.7, 5001. So this is what reaches here. Now, as soon as you get a response, it will look at the destination address and the port number, check are there any entries. Because this port number is associated with this destination IP address, it knows that it needs to change the destination to 10.0.0.1 and 3345 as soon as the packet comes on this side. Right? So finally, the packet will look like this. Source is 128, 119, 40, 186, 80. Destination is 138. Sorry, the destination is what? 10.0.0.1, 3345. So when you're sending a packet from your computer to a remote location, for every packet, this process happens. So imagine the complexity of your router or your campus network edge router. It has a huge table, and it needs to do this address translation time and again. In this way, they're able to reuse these addresses, and they're able to allow communication outside also. This was just in the context of network address translation. Right? So essentially, this is what a middle box does. Why is this weird? Because this is also taking into consideration the port number, which is layer 4. A router is not supposed to do that, right? A router should only look at layer 3. So in a lot of ways, they break the usual conventions of communication according to the protocol stack, and they provide additional functionality. So the next question is, so we spoke about internet ossification, right? So I think you'd be knowing what ossification is at this point, right? So which of the following aspects is not the reason for internet ossification? Is not the reason. Is evolution of newer internet technologies the reason for internet ossification? No, it is not the reason, because newer internet technology tries to break the ossification. So it's contrary actually. The widespread adoption of TCP/IP stack and socket APIs. Yes, you've already adopted what is there so much widespread that you cannot change it that easily, right? So this is true. Competing interests of the stakeholder. Yes, we spoke about this. Proliferation of various middle boxes in the network. Yes. So what I failed to say in the last time was these middle boxes also contribute to internet ossification, because these middle boxes also work on existing protocols. Now, if you change anything in the existing protocols, then the middle boxes all have to be completely changed. And the cost of these middle boxes are quite high. They're not cheap by any means. They run into lakhs and crores in a lot of ways. So the answer to this question is evolution of new internet technologies. This is actually against internet ossification. Right? And question number 10. This is question number 10. So which of the following is not a solution to break the internet impasse? The internet impasse. So what is this internet impasse? So essentially, internet impasse is nothing but the difficulty for innovation. Difficulty for innovation is called the internet impasse. So which of the following is not a solution to break it? So we have to break the impasse. Why is the impasse happening? Because of ossification. So network address translation, we just spoke about it. How is network address translation a solution to breaking the internet impasse? It has nothing to do with internet impasse, right? So in a lot of ways, this is a very localized concept, and this is not a solution. Network virtualization, software-defined networking, overlay networks. These are all concepts that are made to increase innovation, increase the ease of testing new protocols on top of existing networks. So network virtualization is one such aspect which if you can visit the video and you can understand what network virtualization is. And software-defined networking will be coming for you in the next weeks. And overlay networks. These are all networks on top of networks, which can be modified to the way that you want it to be. So in a way, you are implementing something on top of existing infrastructure in order to break the internet impasse, right? So that's pretty much what it is. So these are all the correct answers, which is not. So this is not. So this is the answer for question number 10, right? So I think this would conclude today's session. If you have any questions, you can ask. I'll be here for the next 9 minutes. If you don't have any questions, you're free to leave the call. Thank you.
Yeah, hello, sir.
Yes, please.
Yes, I am Yahya.
Yeah, hi. Hi, yeah.
Yeah, this is my first time of attending lectures. I did not attend all the other previous lectures, and then I think you have done some assignments before.
Right, exactly. Yes.
Yeah. So, and then those assignments are, if you open them, it has told that you have been already submitted, so you cannot make any assignments or whatsoever for now.
Okay, so you're not able to submit the assignments, right? Because the due date is passed.
Yeah, the due date has passed because I just joined not long ago, and then I don't attend any of the lectures. This is my first lecture so far.
Okay. All right. Okay, that should not be a problem, right? I mean, so are you going to take the exam at the end of this course?
Yes, I'm willing to take the exam.
Right. But you have not attended the first few assignment. You've not submitted the assignment, right?
No, I've not attended any assignment yet.
Okay.
Yeah.
So are you concerned that will cause an issue, or is it just a remark that you're making?
Well, my concern is whether it's the math issue and at the same time the basic understanding from unit 1 up to the current unit you are.
Can you just repeat that?
I mean,
Uh-huh.
the lectures that have already been covered from week 1 to now.
Right. Okay, yes.
Yes, because I don't attend all those lectures, so I don't have their basic understanding in those ones yet, unless if I go to the previous videos and then watch them.
Right.
Yeah.
But if I may offer my suggestion or advice,
Okay, sir.
that you take a look at the official videos of NPTEL, right? Week 1, week 2, week 3, and week 4, right?
Okay.
They are more than sufficient to
Okay.
answer the question. To
Okay.
understand the basic ideas. So right after you look at those videos, you
Okay.
can do the link.
Okay.
Just let me just see which link it is. If you go to your place, there will be just give me a moment.
Okay.
Right. So there's a link called problem solving sessions.
Okay.
Right. So if you click on that link,
Yeah.
you will be given access to, I mean, you'll be taken to a Google Sheet, right? In that, you have the presentation folder link where everything that was discussed,
Okay.
the questions that were discussed, is listed out there in the presentation folder link, right?
Okay.
And you also have the YouTube link of all these recorded sessions.
Okay.
Right? So you can take a look at it, but each session is 2 hours long and it is not exactly crisp and to the point. It talks about a lot of basics and it might go from there. So the priority in which you possibly handle the situation is look at the official videos, which are the official
Yeah.
videos, then
Okay.
go to the presentation folder link and
Okay.
take a look at the previous questions. So these previous questions, if you can answer it, well, if you cannot answer it, go to the YouTube link and watch either of our videos. There are two people who are taking care of this course. It is Ranjita as well as myself. You can take a look at her videos or my videos. It doesn't matter.
Okay.
So only for those questions that you don't understand the answer to or you want to know the answer to, and
Okay.
right after that, I think you'll be good enough to answer any question that comes into your final exam as well. So
Sure. No problem. Thank you so
that's
much for the help.
you can pick up for the first week to fourth week. Although put highest
Mhm.
concentration on the official videos. That's my suggestion. Right?
Okay,
That
sir. No problem.
most of the questions.
Thank you so much. I appreciate it.
Sure. Okay. All right, I'm concluding the call. Thank you all.